Let us re-demonstrate with our theory. Suppose that for every excess demand function, like this z, which is continuous, it verifies the strict variance law, in order to be interpreted as an excess demand function, of course. Or if for every excess demand function there is at least a p star, which is an equilibrium, every excess of demand is non-positive, then for every function f, which is for every continuous function f, which is defined delta and takes values in delta itself, there exists at least a fixed point. Existence of equilibrium implies a existence of fixed points. Well, let us consider any function f of this type, and by means of f define the following function z. Z of p is equal to f of p minus p times f of p on p squared times p. Is it clear? This is a simple definition. Simply a definition. But it's important to note that this function z, defined by means of the original function f, is in reality an excess demand function. In other terms, it verifies strict variance law. In effect, if you multiply both sides of this equality by p, you obtain p times z of p, here p times f of p, and here you obtain p squared. Simplify p squared and p squared, and so you have p times f of p minus p times f of p, 0. So this function, constructed with by means of the original f, it is an excess demand function, which verifies strict variance law. Is it clear? Now, by simply applying our assumption, we conclude that there exists at least a price system P star such that every element of an excess demand vector is non-positive. In other terms, a free disposal equilibrium. This means that for every I, for this P star, this vector must have all non-positive components. Or in other terms, that for every I, Fi of P star is less or equal than this real number. It's simply a way to rewrite the inequality, this inequality. Well, in order to prove this theorem, it's sufficient to show that each of these weak inequalities is in reality verified as an equality. So suppose for every I this equality holds, then sum side by side every of these n equations. You obtain sum of Fi of P star equal to this scalar times sine of P star I. But since both P star and f of P star are elements of delta, you have that the sum of this Fi of P star is 1, and also the sum of this P star I is 1. And so you obtain that this coefficient, so to speak, is equal to 1. But if this coefficient is equal to 1, you obtain Fi of P star equal to P star I. P star is a fixed point for the function f. So, in order to conclude the proof, we must prove that it is not possible that this weak inequality is verified for some good as a strict inequality. In effect, suppose ab absurdum that there exists a good I such that this inequality is strict, so we obtain this result. But remember, the meaning of the difference between Fi and this term is nothing but the excess of demand of good I. So this means that in equilibrium, the excess of demand of good I is negative. In other terms, good I is a superabundant good. But if these were true by one of our previous theorems and by strict variance law, we should conclude that the price of a superabundant good is zero. You remember, every superabundant good in equilibrium has a null price if strict variance law is verified. But this is impossible. Look at this inequality. If P star I is zero, this right-hand side is zero, and so Fi of P star would be a negative number. But this is not possible, since F takes values in delta, and so F of P has all non-negative components. Contradiction. So every inequality is in reality an inequality, and the existence of a fixed point is demonstrated. Well, it's not a simple theory. The mathematics is elementary, but there are many steps in the proof. You must put attention to every one of these steps. Well, this concludes the analysis of the simplest case. There is an excess demand function instead of excess demand correspondence. But since in reality individual choices are not, generally speaking, unique, you must consider also the case of a correspondence. And if you return to the regional large Z, the correspondence, excess demand correspondence, it is not possible to reapply this type of proof also to the general case. It is necessary to follow another path, a more complex path. We shall prove the simplest of the theory, or the existence theorems, when there is an excess demand correspondence. But before proving the theorem, we must introduce a mathematical concept, that of a convex hull of a set. Sorry, a moment. I can't see. Take any set A in the n-dimensional Euclidean space. Say, this set. Clearly, this set is not convex. However, there are convex sets which totally include this set A. One of these is clearly the entire n-dimensional space, but for example, this set, which is convex, clearly includes A. Also, this set, which is convex, includes A, and so on. There are many, an infinite number, generally speaking, of sets, of convex sets, which includes A. There is a family of convex set, say Ci, where I belongs to a certain index set. Every element of this class of sets is convex and includes A. Is it clear? Well, you remember by a course in advanced mathematics that the intersection of any class of convex sets is a convex set. Is likewise a convex set. So if you consider the intersection of all the convex sets, which includes A, you obtain another convex set. Since A is a subset of every Ci, A will be a subset also of this intersection. This set is the smallest convex set which includes A. And it is termed the convex half of A, or convex closure of A. I repeat, the convex half of A is the intersection of all the convex sets which includes A, and can be interpreted as the smallest convex set which includes A. How to represent this convex half, which is denoted in my text with this symbol, convex half of A? Simply by filling all these zones, by adding these zones to the original set A, in order to obtain a convex set. Graphically, I repeat this. If you have this set A, the convex half is obtained this way. By adding to original A the smallest area which guarantees in the hand to obtain a convex set. This is Co of A. Is it clear? This is nothing but a definition. The convex half is the intersection of all the convex sets. It is easy to prove that this is the smallest convex set which includes A. Moreover, if A itself is a convex set, obviously it is equal to its convex half. Evidently, because the smallest convex set which includes A is A itself, in the case in which A is convex. Is it clear? There are many theorems which regards this convex half. For example, one of the theorems we shall use in our proof is the following. If the original set A is compact, then also the convex half of A is a compact set. When you pass from A to its convex hull, you obtain another compact set. This theorem is in turn based on the so-called Kara-Theodori theorem. Which tells us the following. Take any set A and consider its convex hull by simply adding this area to original A. Every element of a convex hull, like this, can be expressed as a convex combination of a certain number of elements of the original set A. In other terms, for every x in the convex hull, there exists certain number of elements of original set A, more precisely. They at most are n plus 1, such that x can be expressed as the convex combination of these points xi, where sum of lambda I is equal to 1. In this case, for example, x can be expressed as the convex combination of only two elements of original set A. The theorem tells us that at most we must consider n plus 1 elements of original set A. In other terms, a number of elements equal to the dimension of a space plus 1. For example, if, say, the set A, the original set A, consists of only of these 3 points, x1, x2, x3. This is A. The convex hull of this set is nothing but this triangle. And clearly, if you consider a point internal of a triangle, you must express it as a convex combination of 3 elements of a set. We are in the plane, so m is equal to 1 to 2, and so you need, in this case, of 3 elements of the original set in order to obtain any element of a convex hull as a convex combination of these elements. But no more than 3. In this case, 2 are sufficient. In this case, you must use 3 elements. Clearly, if you have an n-dimensional Euclidean space and not the plane, you need, for example, m plus 1 elements of the set. By means of this theorem, you can prove the previous result. If A is a compact set, also its convex hull will be a compact set, and so on. There are many theorems about the convex hull of a set, but to our purposes it's sufficient to remember these elementary results. Now let us have another short break, and then we shall prove the existence of equilibrium for excess demand correspondence.